Every single day, you use an invisible engine that makes the entire internet feel fast, almost instant. It's called caching. And for about 60 years, it has been one of the most important fundamental ideas in all of computing. So what if I told you that entire engine is on the verge of becoming, well, obsolete? Not because it failed us, but because it's about to evolve into something so intelligent, so predictive, that it pretty much just disappears into the background entirely.
To really get our heads around that future, we first have to understand why the cache was even born. You see, it wasn't created for convenience. It was a desperate solution to a crisis that nearly brought the entire field of computing to a screeching halt.
Okay, so our story kicks off back in the 1960s. This was the golden age of computing, right? Mainframes were getting incredibly powerful, and it felt like the possibilities were just endless. But under the surface, this giant chasm was opening up, threatening to swallow all of that progress whole. The problem was this really fundamental imbalance. It was first spotted in 1965 by a computer scientist named Sir Maurice Wilkes. He came up with this idea of a slave memory, a concept that IBM would pretty soon after put into commercial practice. So what was this huge crisis? Well, it was actually pretty simple. Processors were becoming blindingly fast, but the memory that was supposed to be feeding them data, it was just stuck in the slow lane. Engineers were literally hitting what they started calling the memory wall. To put that in perspective, IBM's top-of-the-line processor could perform an operation in just 80 nanoseconds. I mean, for the time, that was just incredible speed. But its main memory, it took over 1,000 nanoseconds to get back to it. That is 13 times slower. The processor was just sitting there, starving for data. And the result of that gap was insane. These multi-million-dollar machines were spending over 90% of their time completely idle, just waiting. A totally new idea was needed, and that idea was the cache. So how in the world does a cache fix this massive speed gap? Well, it works by taking advantage of a very simple, very predictable truth about how computer programs, and honestly how we as people actually behave. It's a principle called locality of reference, and the best way to think about it is like a chef in a kitchen. The most common ingredients, salt, pepper, oil, they're kept right there on the countertop, not in some distant pantry. That's called temporal locality. You're reusing things you've just used. And ingredients that you often use together, like, say, oil and vinegar, they're kept right next to each other. That's spatial locality. The cache is just the computer's countertop, a small, super fast place for whatever it's most likely to need next. But this simple idea creates a huge fundamental trade-off, especially when you're writing data. Do you play it safe with a write-through strategy? That means you're writing to the cache and the main database at the same time. It's consistent, but it's slower. Or do you live on the edge with write-back? You get incredible speed, but you're risking data loss if the system crashes. This choice, speed versus safety, it's a constant battle in system design. And that exact trade-off is at the very heart of how the biggest internet companies on the planet operate, building systems that can serve millions of us every single second. I mean, just take Netflix. At its peak, their core caching system, which is called EVCache, handles over 30 million requests every single second. Let that sink in. Now, Netflix's genius here is a dual strategy. For the huge movie files, their Open Connect network is proactively caching popular shows inside your local internet provider's building, often overnight. The movie is literally waiting nearby before you even think about hitting play. Then for everything else, your recommendations, your viewing history, their EVCache system uses a global in-memory cache to make the UI feel super snappy. Two different problems, two perfectly tailored solutions. Or look at X, the platform we used to call Twitter. Its timeline has to serve a mind-boggling 300,000 read requests every second. No normal database could ever handle that kind of load. So X's solution is to do all the hard work up front. When somebody tweets, the system fans out that tweet into the pre-made cached timelines of all their followers. That makes reading your timeline incredibly fast. But here's the really surprising part. Over a third of their cache clusters are write-heavy. They're actually using the cache as a high-speed nervous system for all their internal services to talk to each other. The cache isn't just a buffer anymore, it's evolving. And that evolution, well, that brings us to the core idea of this whole explainer. The cache as we know it, this reactive system that just waits for things to happen, it's about to be replaced by something far, far more intelligent. I mean,
Think about it. What if waiting for a cache miss, waiting for the system to fail to find something, is the new bottleneck? What if a system could know what you need before you even ask for it, and just have it waiting for you? This is a massive shift in thinking. We're moving from a rigid, centralized model, kind of like a central nervous system, to a decentralized, self-organizing one, almost like a mycelial network, a mushroom network. The intelligence is no longer in one central place. It's an emergent property of the entire network.
And look, this won't happen overnight. It's going to be an evolution, probably in 3 phases. First, AI will just augment the caches we already have, make them smarter. Next, systems are going to become proactive, predicting our needs and staging data out at the network's edge. And finally, the cache will just dissolve. It'll become an ambient background property of the intelligent network itself.
The potential here is huge. Research is already showing AI can boost cache hit rates by 20% and slash latency by 40%. But there's a risk. Bad predictions waste a ton of bandwidth by fetching data that nobody ever uses. The system doesn't just have to be speculative, it has to be truly intelligent. And this is the ultimate destination, the big takeaway. The cache is going to stop being a noun, a place where data lives, and it's going to become a verb, an action. The network itself is constantly caching data, making it appear just in time, right where you need it. The hardest problems are no longer solved by developers, they're just managed autonomously by the network. This future promises an internet that feels instantaneous, almost telepathic, but it leaves us with a really crucial question. When our entire digital world runs on what an AI predicts we will ask for, who owns that prediction? And what does that mean for our own autonomy? That's the conversation we all need to start having right now.